as a reminder, this is being recorded. So, WizardLM, empowering large language models to follow complex instructions. So the overall goal of this is trying to improve specifically GPT 3.5 Turbo's ability on, oh sorry, not GPT 3.5 Turbo, they're fine-tuning their own model, but specifically an LLM and trying to fine-tune it to be better at following and achieving open domain instructions. However, the existing problem is that creating high-quality instruction data with varying tasks of varying difficulty is just very time-intensive and human labor-intensive. Also, based on the kind of like temp workers that firms usually get to produce data for training, usually they don't have the skills or education required to produce and write really high complexity instructions for complex tasks, like writing code. So the idea behind WizardLM is they take an existing instruction set from previous model trainings, specifically Alpaca and Vicuna, and then they go through an iterative evolution process where they ask the LLM with the prompt that we'll get to in a bit to take the instructions already exist in the data set and then rewrite them to be better. And by better, there are several different metrics by which they measure the evolution of instructions. And then they also then have a model evaluate whether the rewritten instruction is better than the previous one. If it is, they move that instruction forward. If it isn't, they put the original instruction back into the training set to be to have variants generated again in the next evolution. In WizardLM specifically, they go through 4 what they call epochs, or essentially evolutionary cycles of improving the instruction sets. Based on human evaluations of only 10 people, so not too much, they find that instructions from WizardLM are superior to human-created ones. Oh, sorry. To clarify, Evolve Instruct is technically the name of the instruction rewriting LLM, and they use those instructions to then fine-tune a llama model, which they call WizardLM. So they talk about they talk about closed domain instruction tasks, which are predefined and explicit instructions for a predetermined assigned task. Previous literature has shown you can fine-tune LLMs quite well if you know what their task is going to be beforehand. The data sets for those tend to not be great because they're also generated by humans. In contrast, open domain instructions, they enable the LLMs to perform much better because they are open-ended, and the LLMs can therefore create more complex variants through this evolve instruct model. So that's what this paper is about specifically open domain instructions for problems that are in an open domain. Yep, and here they mention that the difficulty distribution of human instructions is skewed towards being moderate to easy, largely just because the human annotators creating these don't have the skills necessary oftentimes to create instructions on the level of complexity they're looking for. So in Evolved Instruct, which is the novel method for using LLMs instead of humans to automatically mass-produce open domain instructions of various difficulty levels, they look at 2 different evolving forms. So starting from an initial instruction, there are two different evolving forms: in-depth evolving or in-breadth evolving. To upgrade or rewrite or I don't know, modify is probably the best word. The simple instruction to a more complex one, or in the case of in-breadth evolving, to completely rewrite it to increase diversity in the instruction training set. So in-depth evolving includes 5 types of operations. So either adding constraints to the instructions, deepening the instructions, concretizing the instructions, increasing the reasoning steps, or complicating the input. Then in-breadth evolving, which is creating a completely new instruction. So the sample that's provided to the model in-breadth evolving is almost like context. So for in-breadth evolving, it's mutation, which is just generally generating a completely new instruction based on the given instructions and the context provided. So those are the 6 evolutionary quote-unquote operations that are implemented by prompt-of LLM. So those are the metrics that they're measuring the instructions by. And as the evolved instructions are generated by LLM, sometimes they'll fail. They use an instruction filter to screen out the failed instruction evolutions, and they do this by engaging other LLM and asking whether the evolved instructions are better on a certain number of metrics. We'll get to that in a bit. So to verify their instruction generation, they fine-tune a llama model to prove that their instructions are superior to existing instruction datasets. So current state-of-the-art works for fine-tuned llama models are Alpaca and Vicuna, and they use those, specifically the Alpaca datasets, as a starting point. And because Vicuna used ShareGPT, which are prompts that people input to ChatGPT and they then share to a public database to be used for training, they also use that as a comparison dataset later on. Yep, they use Alpaca's initial training dataset, which is generated from 175 manually selected seed instructions that were written by the researchers at Stanford. Then they execute 4 evolution epochs with using the OpenAI ChatGPT API, and then through 4 epochs, they end up at the end with 250,000 instructions. So from instructions from evolve instruct, which are the evolved instructions they're talking about here, are superior to the ones, the human created instructions from ShareGPT. It's not that surprising considering humans, especially those using ChatGPT, just en masse, you're going to get fairly simple and low complexity instructions just by a public data set. Labelers or human evaluators prefer the outputs of WizardLM, which is the llama fine-tuned model resulting from the evolve instruct produced dataset. Human evaluators prefer WizardLM over outputs from ChatGPT, less so on the more moderate to moderate difficulty questions, but particularly for the high complexity questions, labelers prefer WizardLM over ChatGPT more so than over less complex instructions, implying that WizardLM specifically excels in the fine-tuning, has correctly created a model that is particularly tuned or able to follow or complete complex instructions. So closed domain instruction fine-tuning. Closed domain is where it's just one specific task, and usually the input data is extremely specific to the task that's being asked of it. Open domain instruction fine-tuning, which is what this paper is about, is much more difficult and open-ended. There's a lot more research on it, and it usually requires much more data because in order to produce an LLM that is truly capable on a generic open domain task, you have to give it such a wide diversity of instructions. And because of that, that's what has motivated this paper to try and create instruction sets using LLM. So the differentiating factor specifically with WizardLM and InstructEvolve, which are both parts of this paper, their differentiating factor is that they use AI generated data from Evolve Instruct. And then unlike Alpaca's self-instruct generation method, Evolve Instruct can control the difficulty and complexity level of generating instructions. We'll get to that in a second, but the distribution of instructions that are resulting at the end of their generation is much better than any other previous instruction data set. As illustrated here, so this is the initial instruction that's given to a model, and then based on whether it's doing in-depth evolving or in-breadth evolving, which is essentially a completely new rewriting, it follows along this path. And then here's the instruction eliminator, which for the instructions that are just being made more complex or having constraints added, they then ask another LLM, which is ChatGPT, they ask it whether the evolved instruction is better or not, and if it's not, then the instruction eliminator eliminates it, and it's thrown out of the set. So the initial data set for instructions D0, indicating at the beginning, is a set of tuples, and the tuples are ik, where k is greater than 1 and less than n, and n is the number of elements in D. So I is the instruction, and R is the corresponding response. In each evolution of, they upgrade all of the instructions in the data set by applying a large-scale language model evolution prompt, and then using a large language model to generate corresponding responses for the newly evolved prompt or instruction. In this way, every time they're evolving the data set, they're also completely filling in all of the responses. So at every step, they have a quote unquote complete involved instruction data set. They're not just iterating on the instructions. For every new instruction, they're also getting the corresponding response from the model. And they note, as it's an open domain instruction data, instructions often have an arbitrary number of inputs and arbitrary number of tasks, and there's no clear boundary between the instruction part and the input, so it can get a bit hazy. As I noted, this is very fitting for AutoGPT, as we have an open domain problem. So their pipeline is instruction evolving, response generated based on newly evolved instruction, and then elimination evolving, also known as filtering instructions that fail to evolve. So pre-trained language models can rewrite instructions to make them more complex and difficult fairly well. They can also create new instructions that are equally complex as the given example instruction, but are completely different. So they're able to create complete original instructions of equaling difficulty to the examples they're given. They also found that through several generations or evolutions or evolutionary epochs, the LLMs can iteratively rewrite and evolve the initial instruction data set with a fairly mediocre difficulty at the beginning through constant enhancement of the initial instruction data sets difficulty level and expanding the instruction data sets richness and diversity. So we'll see it later on, but every evolutionary cycle does improve the prompts a little bit. So the compounding effect does work for instruction evolution. So for each evolutionary epoch, for all the instructions that have been upgraded and those upgraded instructions have been accepted by the evaluation model, they then remove all of the previous versions of those upgrade instructions from the data set. So there would never be within the data set both an upgrade instruction as well as its like child, if that makes sense. But if the upgrade instruction is rejected by the evaluation model, then they just put the initial instruction back in the data set for the next evolution to try it again. So this is the specific prompt for in-depth evolving. It's a bit odd. So I want you to act as this is the prompt for ChatGPT. I want you to act as a prompt rewriter. Your objective is to rewrite a given prompt into a more complex version to make these famous AI systems, example ChatGPT and GPT-4, a bit harder to handle. I didn't understand the sentence or why it would be useful to LLM. As it implies the metric is to make AI systems harder to handle. But anyways, more prompt examples. Yeah, prompts of in-breath evolving. They essentially say draw inspiration from the given example prompt and create a brand new prompt. The new prompt should belong to the same domain as the example prompt, but be quote unquote even more rare. I thought that was an interesting prompt engineering word choice. So they also use their LM to generate corresponding responses for every involved instruction, and then add that tuple of instruction and response back into the instruction pool for the next generation evolution. Also, for the initial data sets, both from Vicuna and Alpaca, for the specific LLM backend they're using, they have their own LLM generate responses to all of the instructions in the initial data set in order to have a comparator, because it wouldn't make sense to compare WizardLM's instruction and response to Alpaca's when that's not the baseline for WizardLM. So this is elimination evolving, or trying to detect evolution failures. So if the evolved instruction does not provide any information increment compared to the original instruction, they consider it to fail. The evolved instruction makes it difficult for large language models to generate a response. They found that when generated responses contain sorry and is relatively short in length, for example, less than 80 words, it often indicates that the LLM struggled to respond to the evolved instruction. So they can use that as a rule of thumb to weed out those evolved instructions. So that's considered another failure case. Or the response generated by the LLM only contains punctuation and stop words or stop tokens. That's another sign of failure. Or the evolved instruction is just a copy of the evolving prompt, or the evolving prompt special tokens and characters, which is just another failure sign that the LLM wasn't actually able to generate anything. So then they fine-tune a model on the evolved instruction set. So after every epoch, they combine all of the different epochs accepted instructions and then mix them all together so they get a normal distribution of difficulty level. Because if, for example, they just concatenated all the sets, there would be differing, or there wouldn't be a normal distribution of difficulty across the entire set, because by the fourth evolution, those instructions are on average more difficult than those in the first evolution. So essentially they just randomize them. And they compare it against ChatGPT, Alpaca, and Vicuna. So they use the OpenAI ChatGPT API to do both the instruction evolution as well as the response generation. They used a temperature of 1, which I thought was worth noting to try and get some variation. I'm not familiar with what the frequency penalty and the top P mean. If anyone wants to jump in and explain that. If not, we can move on to training details. They used a pre-trained Llama 7 billion model. They used the Atom Optimizer, which I'm not sure which it means. And the batch size is 8 for each GPU. They used 8 NVIDIA V100 GPUs with DeepSeed 03, which again, I'm not familiar with. So of the 250,000 instructions, they take a sample 70,000 instruction subset to train WizardLM on. And then for evaluation of the WizardLM model, they had a temperature of 0 and a top P of 0.9. So they made a data set of real world tasks. I found it interesting that they analyzed the data and identified 29 distinct skills that quote unquote represent the main requirements of humanity, which kind of sounds like they've distilled everything humans could need in 29 distinct skills, which is fewer than I would have expected. They found that Vicuna's test data set had a much smaller skill set or set of skills tested. I would assume this is because they use the shared GPT data set, and average people using ChatGPT have a fairly, or tend to be using it for similar things, which leads to a lack of diversity in that data set. So this is the count of tasks per skill in the final Evolve Instruct dataset that they produce in this paper. And then this is the skills distribution of the Evolve Instruct dataset from this paper, the Self-Instruct dataset from Alpaca, and the Vicuna dataset, which is shared GPT data. So you can see that there are specifically many more difficult tasks. So this is the x-axis is a scale from 0 to 10, with 0 being easy and 10 being very difficult. So it's clear that Evolve Instruct is able to produce much more complicated and complex instructions. So they used 10 quote-unquote well-educated annotators to rate responses from Alpaca, Vicuna, WizardLM, and ChatGPT. They shuffled the examples, and the metrics they had the annotators judge the responses on were relevance, knowledge, whether the model is knowledgeable, the model's reasoning ability, the model's calculation ability, and the model's accuracy. They then have the human evaluators rank the responses from 1 to 5, and they allow responses of equal difficulty or quality to be scored equally. So WizardLM and Vicuna, for example, could both get a score of 3. So this is the manual evaluation by humans, um, and this is on the entire data sets. So out of alpaca, or compared to alpaca, WizardLM wins a lot of the time, or either tie. With Vicuna, it's about the same, although Vicuna appears to be better than alpaca, but still inferior to WizardLM. Although ChatGPT is still superior to WizardLM when evaluated on the entire instruction dataset, but specifically when human evaluators were asked to evaluate high difficulty instructions, that's specifically when WizardLM really started to shine, quote unquote, um, and its lead over Alpaca and Vicuna, as well as ChatGPT, narrowed. So WizardLM specifically is specialized and does uniquely well on high difficulty, high complexity tasks. Oh yeah. So this is I guess, is it stem and leaf or tree and leaf? Uh, Essentially, this is the difficulty and complexity level of each data set. Um, I assume this is the standard deviation lines. Uh, so really what's worth noting is specifically that C1 is the first evolution, C2 is the second evolution, and you can see that um, from evolution to evolution, the difficulty and complexity of the data set as a whole is increasing, which means the instruction evolution is working. And you can also see that here, where specifically with the most complex and difficult tasks, uh, their ratio within the entire data set increased as the evolutionary cycles went on. Yeah. Moreover, the depth of the instructions increased significantly with each iteration of the evolution process, which indicates the scalability of their evolutionary method. So as as an attempt to evaluate the instruction sets, they examine the semantic breadth of the different sets of instructions from the shared GPT, Alpaca, and the instruction set they created in this paper using Evolve Instruct. To measure this, they employed the BERT model to produce embeddings for each instruction. The embedding captures the semantic content in a high dimensional vector. So uh, two vectors that have a closer distance are more semantically related to each other than two vectors that have a greater distance between each other in this high dimensionality space. They then take those high dimensionality vectors and utilize a TSNE algorithm to dimensionally reduce them to a two-dimensional space. That allows them to plot uh, these and like the semantic representation of the instructions on a plane, which we'll be able to see. And lastly, they apply a k-means algorithm to partition the data set of instructions into 20 clusters based on their distance within the two-dimensional space. So you can see that shared GPT and Alpaca are quite clustered um, in that most of the instructions are very similar, and there is a lack of diversity in the instruction data set. Compare that to the first evolution, the second and third and the fourth. Um, and they claim that it's possible to see C1 to C4, that the instruction data sets become more diverse and distributed across difficulty and like domain. I think it's a bit difficult to see that, but so they observe that LMs are bad at things like math, code reasoning, and complex data formats, which isn't a surprise to anyone using AutoGPT. So with WizardLM demonstrates a significant improvement over state-of-the-art models, specifically on high difficulty and complexity tasks, which shows that uh, fine-tuning models benefit from having a more diverse and complex and diverse instruction training set. The responses of WizardLM after being trained on this diverse instruction set are more accurate, logical, and knowledgeable than the baselines. The rest of the paper is mainly just examples. We can go over them, but I think we should talk about the paper and the concepts first. So if anyone has any thoughts or additions they'd like to make, questions?
Did comment earlier that I tried the prompts from the in-depth and in-breadth evolution examples, and there wasn't much difference in the output. The output was kind of random, and maybe because I used GPT-4, I wonder why they took this particular path as opposed to just using a seed word, I don't know, math or addition or something, and generating 15 different random prompts that could have also given the same output. Because I thought there's some context that's retained throughout that chain that they showed, but seems like it isn't. So I'd be curious to see what exactly is in the data set more than anything.
Uh, the initial data set that came from Alpaca.
No, the data set, I mean, I guess the data set, when I say, if you go back to that diagram that shows in depth and in breadth, yeah, like what is the output at the end of 1 and 2 and 3 that gets into that instruction pool? Like, what are the different sets of instructions that get into that instruction pool? I don't know if there's an example in the paper on that.
Oh, so which part of this cycle are you specifically asking about? Like 2 to 3?
So my understanding is, if you go back to that prompt they gave uh, ChatGPT for in-depth, let's take in-depth evolving for example, right? Like if
Yes.
you give, yeah, this one, right? It says, I want you to act as a prompt rewriter, and here you have to give a prompt at the end where it says, here is his instruction. And when ChatGPT actually gives the rewritten prompt, that's completely different from the given prompt. And the same thing goes for in the in breadth evolution. It's either, I think in depth is a little similar, but in breadth is different. And so I'm,
So so
oh,
in
go ahead.
breadth is supposed to be totally different because the prompt for in breadth is create a completely original instruction that's in the same domain as the example you're given.
Okay. And in
Right.
depth is still supposed to be similar, right? But in depth wasn't, like, for example, I asked what is 1 plus 1, which was the example up in the paper, and it gave me something different even for in depth. But maybe that's because I'm using GPT-4 and that needs a different way to give this, which is why I was more interested in, given the initial given prompt, what are the sub prompts that were generated that ended up in the instruction pool? So I don't think they gave examples of that here.
Um, so of the general instructions, only the ones that pass the evaluation by ChatGPT are included in the instruction data set for the next evolution. So, for example, when you didn't get back the answer or the answer you thought you would, that answer would, or that new evolved instruction would likely be failed by ChatGPT during the evaluation or evolution evaluation stage, which
Oh, I see. Is that the elimination stage? Is that what it, the instruction elimination stage, or It's a
Yep.
separate stage.
Yeah.
Got it. I see.
Yeah. So that's how they're filtering. Um, and I think if I'm remembering correctly, they queried ChatGPT uh, like 600,000 times, but by the end only had 250,000 instructions, which means there's a very high failure rate.
Hmm. I
I think
wonder how
also
it compares. Oh, go ahead.
the example instruction they gave of 1 + 1 is not a great example to try yourself, just because I think ChatGPT won't understand what you're trying to ask it for. But
Yeah, and I
what were you
wonder
gonna
if
say?
I was going to say, I wonder if ChatGPT itself is complicating the prompt before giving us the response, especially with the difference between GPT 3.5 Turbo and 4. I see that the way it interprets the same prompt is sometimes different.
Oh yeah,
And so I'm
prompt
wondering,
engineering is oftentimes not transferable.
yeah,
But yeah, I imagine that it's having or ChatGPT has a significant effect on I guess the instruction generation.
yep.
Anyone else? I guess if not the reading session, I guess we've read through the paper, so this is the end of the reading group for today. Thanks for all coming. We'll be reading another paper on Friday. I'm forgetting the exact title, but it'll be in the GitHub repository in a little bit.